So this circuit shown here is the basic AC to DC converter. It is okay for low power applications, but for hyper applications we need to better utilize the input source. This circuit uses only the positive half of the input source to draw power and energy. We should also utilize the negative half of the input source to draw the power. So for that we need to add few more diodes so that the negative part is also rectified and put to the output. So let me draw one more diode here. So by drawing this diode, when the input source is positive, so we will see the flow of current through these diodes in this fashion. Right now there is no change in the circuit and its operation except that we have added one more diode. But this diode is important because it will steer the currents during the negative half. When the input source goes negative, so when the input source goes negative, we see that this part becomes positive, more positive than this, and we would like to route the current in this fashion through this diode, through the output capacitor and the resistor, and then have one more diode in this fashion and go through to the source this direction. So when the source is positive, the black colored diodes are used, and when the source is negative, the green colored diodes are the ones which are active. So this is in the literature you will see that this circuit is written more commonly in this fashion, easier to visualize. So you see the diodes and the capacitor and the load are in the same way, and you have the input source connected to the middle portion of the bridge. All right, this is called a bridge circuit. So this is V in. So I'll name this as C R naught. This is V naught. This is I. This is IC, and this is I naught. So when the input source V in is positive, so this will be positive. The black diodes are the operative ones, and you will see the arrow mark, and you will see the current flow in that direction. When the input source is negative, which means this end, the arrow end I am showing here, is more positive than the other end, and you will see that the current flow will be through the green diodes and in the same direction through the output circuit, then flow back in this fashion. So this is how the full bridge rectifier operates, and here both the positive part and the negative part are utilized. So therefore you will see the ripple is lesser, or for a given ripple the capacitance size will be smaller. So let us also look at the waveforms. The capacitance value waveform will change, and very minor change in the diode ratings. So let us have a look at the waveforms. So if you see in the half wave rectification circuit, the negative power portion was not utilized. So now in the full bridge circuit, the negative portion is also getting rectified and utilized. So this also will become part of the output for filtering purposes. So if the capacitor was not there, this would be the wave shape of the output. And now that the capacitor is present, it will filter, and the wave shape will be something like that under steady state conditions. So you will see that the capacitor follows the input here, and then the capacitor discharges on its own depending upon the load time constant. The input would have gone down and it will come up and then again intersect here. The capacitor will follow till this point and get recharged, and then again so on the wave shape repeats. What you have to notice here is that this the ripple frequency has doubled. So in the case of the half wave rectification, the ripple frequency was same as the input frequency, but now because of the rectification I have now one more extra half sine wave coming in here, so the ripple frequency is doubled, and as a consequence we have advantages. So let us look at the current wave shapes also. Let me put these time markers here. This is the point of intersection, a time marker here. The peak value, a time marker here. Again, point of intersection of the capacitor voltage and the input, so on, like this. So if you see in the case of when the input voltage is positive, this diode and this diode conduct, or in this circuit this diode and this diode is conducting, and therefore the current flow through the diodes during this period is this, and there is one during this period. So this is for the positive half of the input wave. So during the negative half of the wave, it is this diode and this diode which becomes active, and so on, these two diodes in the circuit which become active, and you will see the current flowing during this part. So this is what the current flow will be here. This is how it will look, and it gets split into the capacitor current and the output current. The average of that will be the I0, which flows through the output resistance R0. So this is I0, and this current I minus I0 will be the current that flows through the capacitance C. So you could find the peak current in the diode in a exactly similar way. There is not much change in the sense that the diode currents will still see currents only during either the positive half for these red marked diodes or during the negative half for the green marked diodes. So let us find out the value of C. This is Im. So let's say this is alpha, the conduction angle for the diodes. We'll mark it as alpha. Peak to peak, this peak to this peak, as a positive peak to the negative peak of the input is pi or t by 2 in terms of time. So let us see the value of the capacitance. There is a slight change in the value of the capacitance that you will see. So we have marked V1 here and V2. These are the two extremities of the ripple voltage. You have the alpha conduction angle t by 2 or pi. So now let us see what is the capacitance value. The energy stored in the capacitor during this point is half C V1 square. It would have discharged to half C V2 square at this point, and all that energy is given to the load. So you will see half C V1 square minus half C V2 square is the energy into frequency will be the power. The frequency here is, now the frequency is 2 times, the ripple frequency you see is 2 times the supply frequency of the mains. So I'll say 2F is the power. So what is the power? P naught. P naught is the average power throughout into the duty cycle pi minus alpha. This is that pi minus alpha divided by pi. P naught into pi minus alpha by pi. Just like how we did for the half wave rectifier circuit. So this can be further simplified. Now this is written in this fashion. C V1 square minus V2 square is V1 plus V2 into V1 minus V2. So V1 plus V2 divided by this 2 into V1 minus V2, which is delta VR, into 2F will be P naught, which is V naught into I naught, into pi minus alpha by pi. The V naught here and this V naught will cancel off. So you have C is pi minus alpha by pi into I naught. This 2 also I will take it this side, I naught by 2 divided by delta VR into F. This is the capacitance equation. You will see that the capacitance here is proportional to I naught by 2, whereas in the other case earlier we saw that it's proportional to I naught. So therefore you will see a reduction in the value of C. Of course, alpha is nothing but cos inverse of V2 by V1. In this case, the PIV of the diode is also reduced. The PIV of the diode is just to be greater than V1, the peak value, because you will see that when this diode is conducting, the voltage across this diode is off, and the voltage across that is max V1 or Vm, max of Vin. When the green diodes are conducting, the red diodes will see max again Vm. So that it should be greater than just greater than the max of the input voltage, which is V1 in this case. The currents through the diode will be same as in the case of the half wave rectifier case. There is no change, all else being same. Let us now try to develop the power supply for a typical electronic system. For digital circuits, the more common power supply would be 5 volts, 3 amps, or 3.3 volts, 3 amps. Typically in the laboratory, you will find laboratory power supplies of 5 volt, 3 amps, 3.3 volt, 3 amps. Of course, for specific circuits on PCBs and electronic systems, the wattage may vary, but generally the voltage will be around 5 volts or 3.3 volts. So we can try to develop the circuit for that. And the case of analog circuits, for analog circuits, most commonly you will see plus minus 12 volts 1 amp or plus minus 15 volts 1 amp. This kind of power supply range that you would see for analog circuits. So typically in the laboratory, you will see power supply boxes having 5 volts plus minus 12 volts or 5 volts plus minus 15 volts, this kind of an arrangement. So let us see how a power supply circuit looks like. We will first develop a linear power supply. Quality wise, the linear power supply gives outputs that is of very high quality in terms of performance, in terms of ripple rejection, in terms of regulation. And therefore, when you are talking of high precision electronic systems, go in for a linear power supply. If you are looking for compactness, then go in for a switched mode power supply. First, let us look at how a linear power supply looks like. Let us make that. Let us design that. So the power is taken from 230 volts mains. So this is a 230 volts mains input, and then it is being passed through a transformer, a step down transformer, because you need to get lower voltages from 230 volts, and the output of the secondary of the transformer needs to be interfaced with the AC to DC converter. And the AC to DC converter, we have just now looked at how AC to DC converter looks like and how to design that. So it consists of a full bridge circuit followed by a capacitor filter circuit, and the output of the capacitor is given to the load, and the load in this case is a linear regulator. So the linear regulator consists of a series pass element like a BJT. It is also called a series drop element. It drops the varying voltage across this, and at the output you have a voltage sensing arrangement. It's a attenuator where you tap off the voltage for feeding back at the center point of this. And the BJT here is driven by a gain block K, and there is a comparator which compares the output voltage which is fed back with a reference, V reference. The actual load is now connected across this. So this will be the electronic load, this will be the electronic circuits that will be powered by this linear regulator. So right now I will replace this electronic load by a resistive load, and that is R0 and V0 here. So that is V0, and you have R1 and R2 here. This will be a V0, attenuated value of V0, where A is R2 divided by R1 plus R2. So this will be compared with the reference, and the error will be passed on through this gain block, which will drive this BJT accordingly, so that the drop across this BJT or the series pass element will get adjusted in such a way that V0 is kept constant. So you know that here the voltage is a DC voltage but has a ripple content, has a high ripple content, and we need this series pass to drop all the ripple contents across it in such a way that V0 is kept constant. So this is how this operates. Now, how do you make a V0 here match with V reference? How to make the error 0? So if I write this error, and this I will call it as the base voltage VB, then let us go through a dynamic situation where under some condition V0 increases, maybe due to change in load R0, due to an increase in the value of R0, or due to variation in the power supply, due to variation in the line. All this can result in variation in V0. So let's say that V0 has changed, V0 has increased. Once V0 increases, the potential here at this point has increased, which implies that the potential AV0 has increased. And because AV0 has increased, this is at the feedback point, negative feedback point, Vref has not changed, and therefore error, which is Vref minus AV0, will reduce. So E reduces, and this gets passed through the gain. VB will reduce, and once VB reduces, the drive to the BJT reduces, and the voltage across this BJT, VCE, because the drive has reduced, VCE will increase. And once the VCE increases, which means more voltage is dropped across the series pass element, this will absorb the drop, increase the voltage drop across this, and try to bring back the voltage here to again its nominal controlled value. So this is how the negative closed loop feedback works, trying to bring back the output voltage or trying to regulate the output voltage to its nominal value. Same thing will happen when V0 decreases. V0 decreases, this will decrease, AV0 will decrease, error here will increase, VB will increase, the drive here has increased, and VCE will decrease and try to bring back V0 to its normal value by increasing it. So this is the negative feedback loop operation that will happen. But our interest is to see that error here goes to 0, which means K should be very high. So error E is equal to VB by K. And how can you make E tend to 0? E will tend to 0 if K tends to infinite value. So as K tends to infinity, then we know that the error will tend to 0, and Vref, AV0 will match Vref, and therefore V0 will be a function of Vref, that whatever we set. This will be set point control. So in order to implement this practically, let us replace this K supposed to be tending to infinity. What is an high gain component? One thing that will come to our mind is op-amp. Op-amp is a high gain component, and this part can be replaced with an op-amp. So let us do that. So I will erase that portion and introduce an op-amp minus plus. Let me make the connection to the minus, and plus will go to the Vref. The power supply for the op-amp will come from here. So let's say this is the ground and this is the supply Vi. This is the unregulated varying DC supply Vi, which we can apply to the op-amp, a single supply op-amp. So this is a circuit that will work. See that this op-amp, this is the virtual ground, AV0, and because of the very large gain that op-amps have of the order of 10 to the power of 8 and so, you will see that VB divided by the very large op-amp gain will almost be 0 here, which is called as the virtual ground, and therefore Vref will be equal to AV0. So because of this negative feedback that is happening, AV0 will follow Vref, and therefore V0 will be regulated. Now let us discuss how to get this Vref. How do you get this Vref? A constant fixed voltage reference. So let us see how do we do that. There is a very simple circuit for that. We will use a Zener. So from this unregulated supply, we'll use a resistor and a Zener diode in this fashion, and across the Zener I connect a resistance. Could connect a fixed resistance like this or a potentiometer and tap off from the potentiometer to obtain Vref of whatever value we need by adjusting this center tap. So this will be Vz and this is Vi, this is Rs, and call this Rr. So there are these three currents. This is the IZ current, this is I0 current, this is IR current. Vi is unregulated. It varies from a minimum value of Vi min to a maximum value of Vi max. So having this kind of constraint, this equation, how do we design the value of Rs and Rr for a given Vz voltage and the input conditions of Vi, where the Vi can vary between Vi and Vi max. So take the Zener diode's characteristic. I will draw the IV characteristic, IV. So this is the forward characteristic, but the Zener is operating in the reverse portion. So this is the reverse characteristic. This is the Vz. This is Vz here. And the current, the Zener current is along this axis. Because you have two extreme points for Vi minimum and Vi max, you have two extreme operating points, possible extreme operating points. One is when Vi is Vi max. When Vi is Vi max, the current that flows through Rs is Vi max minus Vz divided by Rs. So let us mark that operating point here. This is Vi max minus Vz divided by Rs. So this is the current that will flow through the Zener if Rr were not there. Let us say Rr is infinite, which means the entire current flows through this Zener diode and it should not blow up the Zener diode. Therefore, you should rate it accordingly. Zener diodes have power rating, power dissipation rating, PZ rating, and you should not exceed that PZ rating, that is VZIZ. So it should be less than PZ rating divided by Vz. PZ rated divided by Vz. So when we are trying to figure out this equation, keep in mind, whenever you select a component like a Zener diode or any other component for that matter, select the component such that the operating stress, it could be current, voltage, power, anything, operating stress should be less than 75% of the rated stress. This is a thumb rule which you can follow so that you have some buffer margin of 25% between the max operating stress and the rated stress, so that the component can withstand some some uncertainties and variabilities. So in this equation, if you see that, which means that Vi max minus Vz by Rs can be set equal to, let us say, 75% of PZ rated or 0.75 PZ rated by Vz, which means that I am going to have this operating point Iz max to be at 75% PZ rated by Vz. So PZ rated is known because I have chosen the diode, Vz is known, Vi max is known, and therefore Rs can be calculated. So this is the value of Rs that you will calculate and use here at this location. Now for the value of Rr, when Rr is infinity, no problem, that you see that the value of the current flowing through the Z is going to be always less than this. It will be anywhere here. So on the upper limit of Rr, there is no issue, but at the lower limit, we need to set and calculate that RR does not go below a particular value. So let us say that another operating point here is when Vi is Vi min. When it is Vi min, the current that is flowing through Rs is Vi min minus Vz by Rs. And if RR were not there, the entire current would flow through Iz, and therefore you will have an operating point like this when RR is infinite. Vi min minus Vz divided by Rs. However, if you want to use RR, you should see that there is a portion of the current that will get diverted through RR, that is I naught. So Iz plus I naught will be IR. Or you can say that IR minus a minimum Iz. What is the minimum Iz? I will say that in the IV characteristic, I will take this point as the minimum Iz that should flow. I will say Iz minimum that should flow in order to maintain Vz, the voltage Vz. Below that, you will see that it will come out of the breakdown region and Vz will vary. So that is not what we want. We want a constant fixed Vz appearing across the Zener, and therefore I will ensure that there is at least a minimum Iz minimum flowing through the Zener. Therefore, what you can pass into I naught is V in min minus Vz by Rs minus Iz minimum. So V in min minus Vz by Rs minus Iz minimum is what I can pass into I naught, and that is the maximum possible I naught that I will allow, worst case condition. So therefore, RR, the minimum value of RR will be Vz by I naught max. I will not go to a value of RR below what is calculated here. So this will become the minimum value of RR. You can choose a value of RR higher than that, such that probably in the middle of this Iz minimum and maximum Iz, you will set the operating point, and RR can be a fixed value here. And then you tap off from RR, if it's a potentiometer, from the center tap, and you can set the value of Vref accordingly here to whatever value you want V0 to be, such that A V0 is equal to Vref. So this way you will set the reference voltage for this circuit. Let us now incorporate the reference circuit at this point. So let me erase a portion there and draw this Zener regulator circuit, the reference, which will give you the reference voltage. So I'll connect a pot here like this and take the tapping of the pot and connect it here to provide the V reference. So by adjusting the tap of the pot, I can get any value of V reference here to match AV0.